What specific problem does your proposed rStar method aim to solve, particularly in comparison to existing approaches like RAP? And why is this an important challenge in the context of reasoning with smaller language models?
The rStar method specifically aims to address the challenges faced by smaller language models, LLMs, in effectively exploring the solution space and accurately evaluating reasoning steps during complex reasoning tasks. Unlike existing approaches like RAP, which often lead to low-quality reasoning trajectories and rely on self-rewarding mechanisms that yield near-random performance, rStar introduces a self-play mutual generation discrimination process. This process enhances the reasoning capabilities of LLMs by employing a richer set of human-like reasoning actions and a mutual consistency verification mechanism using a second LLM as a discriminator. This is crucial because LLMs, due to their limited capabilities, struggle with traditional self-exploration methods, making it difficult to generate high-quality solutions and accurately assess their correctness. By improving the reasoning accuracy of LLMs, rStar not only enhances their performance but also broadens the applicability of neural language models in complex reasoning tasks.
How does the proposed rStar method work? Please illustrate the methodology step by step, including the roles of MCTS and mutual consistency in the reasoning process.
The proposed rStar method enhances the reasoning capabilities of smaller language models, LLMs, through a structured process involving Monte Carlo tree search, MCTS, and mutual consistency. First, rStar decomposes the reasoning task into a multi-step generation process where MCTS is employed to explore a rich set of human-like reasoning actions, such as proposing sub-questions or rephrasing the original question. This allows the LLM to generate diverse candidate reasoning trajectories. Second, to evaluate these trajectories, rStar introduces a mutual consistency mechanism, where a second LLM acts as a discriminator, providing unsupervised feedback on the generated trajectories. The discriminator completes the reasoning steps based on partial inputs and checks for consistency with the original trajectory, thereby validating the quality of the reasoning. Finally, the best trajectory is selected based on a combination of the reward from MCTS and the confidence score from the discriminator, ensuring a robust reasoning process that significantly improves accuracy across various tasks.
Can you provide a simple yet illustrative example that showcases the inner workings of rStar? Specifically, walk through the actions taken during a reasoning task using rStar and explain how it leads to a final answer.
To illustrate the inner workings of rStar, consider a reasoning task where the goal is to solve a mathematical problem. Initially, the target LLM, let's call it LLM1, starts with the root question and employs the Monte Carlo tree search, MCTS, to explore potential reasoning actions. For instance, LLM1 might first take action A3, proposing a sub-question related to the main problem and providing an answer. If this answer is deemed incorrect, LLM1 can then utilize action A4 to re-answer the sub-question, ensuring a more accurate response. Next, LLM1 may use action A5 to rephrase the original question, clarifying any misunderstood conditions. Throughout this process, a second LLM, LLM2, acts as a discriminator, providing feedback on the reasoning steps generated by LLM1. If LLM2 agrees with the final answer derived from the reasoning trajectory, this mutual consistency reinforces the correctness of the solution. Ultimately, the trajectory with the highest score, based on the rewards from the MCTS and the agreement from LLM2, is selected as the final answer, demonstrating how rStar effectively enhances reasoning capabilities through structured exploration and verification.
What are the theoretical or practical benefits of using rStar over traditional approaches for enhancing reasoning in LLMs? In what ways does it improve efficiency or accuracy?
The rStar approach offers significant theoretical and practical benefits over traditional methods for enhancing reasoning in smaller language models, SLMs. Firstly, rStar decouples reasoning into a self-play mutual generation discrimination process, which allows for a richer set of human-like reasoning actions, enabling SLMs to explore diverse reasoning paths more effectively than traditional methods that rely on a single action type. This leads to the generation of higher-quality candidate reasoning trajectories, as evidenced by the substantial accuracy improvements on datasets like GSM-8K, where Llama 2-7B's accuracy increased from 12.51% to 63.91%. Secondly, rStar employs a mutual consistency mechanism, utilizing a second SLM as a discriminator to provide unsupervised feedback on generated trajectories, which enhances the accuracy of the reasoning process by validating candidate solutions through peer agreement. This method not only improves the overall reasoning accuracy, but also avoids the pitfalls of overfitting associated with traditional reward models, thus making the process more efficient and reliable across various reasoning tasks. Overall, rStar demonstrates a marked improvement in both efficiency and accuracy, surpassing the performance of existing self-improvement techniques like RAP and self-consistency.
How was the effectiveness of rStar validated or tested? Describe the experimental setup, datasets utilized, and the metrics used to demonstrate its performance compared to baseline methods.
The effectiveness of rStar was validated through extensive experiments involving 5 small language models, SLMs, Phi-3 Mini, Llama 2-7B, Mistral 7B, Llama 3-8B, and Llama 3-8B Instruct, across 5 diverse reasoning tasks including mathematical datasets like GSM-8K, GSM Hard, Math, SVAMP, and a common sense reasoning task, Strategy QA. The experimental setup involved performing 32 rollouts using the Monte Carlo tree search (MCTS) algorithm to generate candidate reasoning trajectories, followed by a mutual consistency verification process using a second SLM as a discriminator. Performance metrics included accuracy improvements on the reasoning tasks, where rStar significantly boosted accuracy on GSM-8K from 12.51% to 63.91% for Llama 2-7B and from 36.46% to 81.88% for Mistral, demonstrating its superiority over baseline methods such as single-round chain-of-thought prompting, self-consistency, and self-improvement techniques like RAP and TOT. The results indicated that rStar consistently outperformed these baselines across all evaluated tasks, showcasing its effectiveness in enhancing SLM's reasoning capabilities.
What specific results were achieved with rStar on the GSM-8K dataset, and how do these results demonstrate the method's potential compared to fine-tuning and existing approaches?
The rStar method significantly improved the accuracy of the Llama 2-7B model on the GSM-8K dataset from 12.51% to 63.91%, showcasing its effectiveness in enhancing reasoning capabilities without fine-tuning. Additionally, Mistral 7B's accuracy increased from 36.46% to 81.88%, and Llama 3-8B's accuracy rose from 47.23% to 85.52%. These results indicate that rStar not only matches, but can even surpass the accuracy achieved through fine-tuning, as demonstrated by Mistral outperforming fine-tuned MetaMath by 4.18%. Furthermore, rStar consistently outperformed various state-of-the-art baselines, including single-round inference techniques like few-shot chain-of-thought and multi-round prompting approaches, such as self-consistency and self-improvement methods like RAP. This performance highlights rStar's potential as a robust alternative for improving reasoning in smaller language models without the need for superior models or extensive fine-tuning.